Hello everybody, welcome to chapter 2.2 part A, and what we're going to talk about today are differentiation rules. We've been through pretty extensively now the limit process to find derivatives, and what this chapter is about is making finding derivatives just a little bit easier on us by applying a few rules that'll work every time. So our objectives for today are to learn and apply some of those differentiation rules. We're going to learn about the constant rule, the power rule, the constant multiple rule, and the sum and difference rules. Alright, so let's get started. We'll begin with the constant rule. And let me make sure you guys can actually read that real quick. And there we go. And what the constant rule says is that the derivative of a constant is 0. And it looks like this. dx with respect to c equals 0 for the function f of x equals c. Okay. And analytically, this makes sense. If we do that limit process for any constant, what we have is the limit as the change of x approaches 0 for c minus c. Right? We have no true f of x or anything to fill in. We just fill in the constant. And then we have over change of x. And then we can say that that is the same as 0 over change of x, which is 0. And that will always be true. And we know if we think about this graphically, say we have the function, I'm not sure, f of x equals 2, the constant 2. Remember that f of x equals 2 is just saying y equals 2. And we know by now that on a coordinate plane, let's call this 2, let's call this 1, 2, let's call this 3 up here. If we wanted to graph y equals 2, we would just draw a perfectly horizontal line through 2 on the y-axis, and we know, let's label this f of x, we know that a horizontal line, the slope is just 0. So that's why it makes sense that our slope here, f prime of x, would equal 0. Alright. Let's talk about another little example that might look a little bit different. So if we were asked y equals k pi squared, and we're given the information where k is an is a constant, then we know if we were to take the derivative dy over dx, which we could simplify as d over dx of our function, would just end up being 0, given we are taking, there we go, sorry guys, given we are taking the derivative of a constant value, and we know pi is also a constant, and our graph would have a horizontal line, which would be a slope of 0. Alrighty, let's talk about the power rule. And the power rule is really interesting. To get a grasp of the power rule, we're first going to talk about expanding binomials. And what those look like every single time when we expand them. So, say we were to have x plus change of x squared Well, we could expand that out as x squared plus 2x times the change of x plus change of x squared. If we had x plus change of x cubed, we would get x cubed plus 3x squared times change of x plus 3x times change of x squared plus change of x cubed. And again, I do highly encourage you to watch that Khan Academy video that I gave you a link to if we're not solid with expanding our binomials. If we had x plus change of x to the fourth, we could expand that out as x to the fourth plus 4x to the third times change of x plus 6x squared times change of x squared plus 4x times change of x cubed plus change of x to the fourth. If we did to the fifth, it would look like this. X plus change of x to the fifth. I'm going to start to write a little bit smaller here so I can fit everything. We would get 5. Oh, not first. First we'd get x to the fifth plus 5. X to the fourth times change of x plus 10 x cubed times change of x squared plus 10 x squared times change of x cubed plus 5x times change of x to the fourth, and then we have plus change of x to the fifth. Alright, there's everything that we can write out there. And it's important that you recognize these come from functions where we would have an f of x, for example. If we were finding the derivative of something like f of x equals x squared, correct? Or f of x equals x cubed, or f of x equals x to the fourth, f of x equals x to the fifth. That's where these are coming from. If we start with the function like any of these in red, then we would start the limit process by applying these following binomials. Right? We would have to substitute in x plus change of x for every x, so we put that to the fifth power. Hence, it's important that we understand how to expand binomials. Okay, that being said, let's talk about what's happening here with this binomial expansion. Let's take a look. I'm going to draw a line through all of this. If we see something, check it out. I'm going to draw some arrows, and I'm going to draw some arrows. Past this point, past this little section I've sectioned off here in green, every single term has a change of x squared. Is always a factor, correct? If you look at every one of these, they all have at least a change of x squared, every single one. And that's going to happen with every binomial expansion. And let's go back to the rest of the limit process. Let's think about two important things that happen whenever we use the limit process to find a derivative. The first thing that we always end up doing towards the very end is that we factor out a change of x, and then we cancel it. So every single one of these change of x's squared is just going to become a single change of x. And then at the very end, we find the limit as our change of x approaches 0. So at the very, very last thing we always do is that we set any change of x's left over equal to 0. So essentially what happens to every change of x squared past this point is it just becomes 0. And so what we can do when we're finding the derivative is just pay attention to these first pieces. And what we can use to describe these first pieces is the following rule. So here's the power rule. Alright, we're going to get a little formal here. We're going to say if n is a rational number, can you see this okay? There we go. Is a rational number, and we have f of x equals x to the n is differentiable, and dx of our function x to the n equals n times x to the n minus 1. So if n is a rational number, then we can say then f of x to the n is differentiable, and the derivative of that f of x is always n times x to the n minus 1. And furthermore, we're going to say here we go, for fancy f, for our function to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. Alright, so we got our formal definition going. Here is the piece we're going to pay attention to the most. Let's do some examples of this. So, if we were to have the function f of x equals x to the third, well, let's identify something. If we're using the power rule to help us, this little 3 right here is our n value, and when we put that into our power rule, what we do is we take that n value, we can say f prime of x equals that n value, 3, times x to the n minus 1, to 3 minus 1, which ends up being 3x squared. Alright. Next example. So if we had g of x equals cube root of x, remember that g of x is saying x to the 1/3. The 1/3 power and the cube root are the same thing. So that right there tells us that our n value now is going to be 1/3. So when we apply that, we find g prime of x. We take our n value, 1/3. We'd use x, and then we want to do 1/3 minus 1. And so we have 1/3 x to the negative 2/3. And we remember the rules of exponents. Now that we have a variable to a negative exponent, we have to move the entire thing to the bottom of a fraction. So we get 1 over 3x to the 2/3. If we do another one of these, yeah, we can see, okay, alright. So if we have y equals 1 over x squared. Well, again, we're going to change this and make sure we're using an exponent so it looks a little bit easier. 1 over x squared is x to the negative 2. That tells us that our n is negative 2. So when we find the dy of dx, that means we're taking the d dx of x to the negative 2. And so then we take that negative 2 and we put it in front, and we say x to the negative 2 minus 1, which we can simplify out to be negative 2 to the x times x. Oh, I keep saying the wrong thing. Times x to the negative 3. Use your rules of negative exponents again, and we get negative 2 on top, and x to the third goes to the bottom. Alright. Let's talk about the constant multiple rule. Constant multiple rule. Alright. Let's go through another one of those formal definitions, get that out of the way. So, if, fancy if our function is a differentiable function, and c is a real number, then c times the function, is also differentiable, and we can arrive at the following rule. The derivative of cf of x equals the constant, our c value, times the derivative of f of x. And that makes sense because if we look at this, the proof of this from the limit process, what we've got going on is the dx of c times our f of x, and we say that's the limit as the change of x approaches 0, and we'd have a couple things going on. We'd have c times f of x plus change of x minus c times f of x all over change of x. And what we can do, you can see from the top, they both have c. We can factor that out. So we have change of x as it approaches 0. We factor out the c, and then we have still f of x plus change of x minus f of x all over change of x. And now we know about limits, that if we have a constant times something else, we can take that constant, we can put it out front. So what we have is our c times the entire limit, times the limit as the change of x approaches 0 for f of x plus change of x minus f of x all over change of x. And pardon me, just really tiny down here, I'm going to write it out finally. What we would end up having then is c times f prime of x. Okay. Let's do some examples of this. So say that we had, let's use y. Y equal to 5x cubed. Well, it's clear that we have 5 times x cubed, so let's go ahead and use that constant multiple. If we were to take the dy dx, if we were to take the derivative of y with respect to x, we would set that up as the derivative of 5x cubed with respect to x. And what we have going on here is we can take that constant, put it out front, so we've got 5, and then we have times the derivative with respect to x of x cubed. And right here, what we know we can do now is power rule that. And so what we end up having is 5 times n comes out front, 3, x, n minus 1 is 2. 5 times 3x squared, we get 15x squared as our derivative. Okay. Next example, if we have, well, let's use blue still, yeah, okay. If we have y equals negative 3/2 x, again, we're going to set this up the exact same way. We're going to start by seeing that we have a negative 3/2 times an x, so we can start to separate that out. Again, we're going to take the derivative of y with respect to x, so we're going to take the derivative of negative 3/2 x, and we put negative 3/2 out front because that's our constant, and then we take the derivative of our x, and again we can use the power rule there to help us. Power rule. And so what we end up getting is negative 3/2. Here our n value, even though we don't write it, is 1. And then we would have times x to the 1 minus 1, which would be 0. And we all know exponents, variables with exponents that are 0, anything with an exponent of 0 is just 1. So I get negative 3/2 times 1, or just negative 3/2. Alright, and lastly, let's arrive at a rule here. You can see that every single time that we had the constant times the power, the constant times the variable, every time that happened, we had to use the power rule eventually. So what we can arrive at from this is that we can combine the constant multiple rule and the power rule. We can combine those into one rule, which says that the derivative d dx of a constant times x to the n is the constant times the power rule, or the constant times n x to the n minus 1. Alright, let's practice this. Oh wait, never mind, we'll practice it in a little bit. Alright, so let's talk about the sum and difference. Rules. And again, let's start off with the formal stuff. So what we're going to say is the sum or difference of two differentiable, there we go, functions, we'll call them fancy f and g, is itself differentiable. What we can say then is that the derivative of fancy f plus g, or fancy f minus g, is the sum or difference of the derivatives of f and g. Let's write this with some numbers so it looks a little bit neater. So essentially, if we're taking the derivative of f of x plus g of x, that is equivalent to adding f prime of x plus g prime of x. If we wanted to take the derivative, it should be d over dx of f of x minus g of x, we can say then that that's the same as saying f prime of x minus g prime of x. Okay. It's important for you to note, there's a little asterisk in here, that the quotients and products do not do this. We can't use this rule and call it good enough for adding and, for multiplying and dividing. We'll cover those in chapter 2.3, but just know that this does not hold for the operations of multiplication and division. Let's practice this though. So let's do some examples. Say that we had f of x equals x cubed minus 4x plus 5. Well, if we use this rule, what we can essentially find is the derivative of each piece, and then we will find the derivative of the entire thing. So, if we use the power rule here for x cubed, we take our n value, which is 3. We say x, and we say to the 3 minus 1, which is 2. Out here, what we have is negative 4 times the derivative of x. And the derivative of just x, you guys, is 1. I could go through the power rule of that again, but just like in our previous example, it's always going to be just the number 1. So what we end up having there is negative 4. And then, remember, the derivative of a constant is always just 0. So now let's take all of these things, let's add them up. Looks like we have 3x squared minus 4 plus 0. So our derivative, we can safely say, f prime of x equals 3x squared minus 4. Let's do another example. So say that we had g of x equals, let's see this, g of x equals x to the 4th negative x to the 4th over 2 plus 3x cubed minus 2x. I'm kind of running out of room. I'd like to spend some more time on this, so I'm going to rewrite it on a separate sheet of paper. Okay. Still doing the same thing. So g of x equals negative x to the 4th over 2 plus 3x cubed minus 2x. There we go. That's a little bit neater. Okay, again, we can just go piece by piece and then add and subtract at the very end of all the separate derivatives. Right here, this isn't very clear to see at first, but if we go step by step, piece by piece here, what we can see is that there's actually the constant, I'm going to write a little red 1 here, negative 1/2. So what we can do is take out negative 1/2 and multiply it by the derivative with respect to x of x to the 4th. Now x to the 4th is a little bit easier to take the derivative of. We can use the power rule there, put our 4 in front. So now we're going to have negative 1/2 times 4x, and then 4 minus 1 would get to the 3rd power. Okay? Over here, what we have is, again, the constant. So we're going to take the constant out in front, 3, and then we're going to take the derivative of x to the 3rd. So if we use the power rule, our n number is 3, put that up front, write x, and then we do the 3 minus 1, which would be 2, and we would get a positive 9x squared. Over here, again, we'd have that constant out front, negative 2, times the derivative of x, which we discussed earlier, is always going to be 1, and so at the end we have a minus 2. Let's simplify this out even further. Negative 1/2 times 4 is going to be a negative 2 x cubed, and I rewrite everything else, plus 9x squared minus 2. So we have arrived at our derivative. We can safely say that g prime of x equals negative 2x cubed plus 9x squared minus 2. Alright. Now what we can say is, well, we'll get to that topic in a second. Let's do another example of this and then I'll show you that. Alright. So if we had y equals 3x squared minus x plus 1 all over x, what we can do here is say that we're going to take the derivative of y with respect to x. So we're going to take the derivative of 3x squared minus x plus 1 all over x. This is a little hard to tell what each piece is. So what we're going to do is we're going to use some algebra and we're going to rewrite this. Understand here that whenever you have the same denominator, right, all over a single denominator, you can just rewrite each piece of this fraction. So what we've got going on is a 3x squared over x minus an x over an x plus a 1 over an x. Now this is a little bit easier to see. What we've got going on is here x's would cancel and we would get just 3x, and x over an x is 1, and then we have a 1 over an x. I'm going to rewrite one more thing here before we start to take the derivative of each piece. What we should understand as well is that we have 3x minus 1, and then we have plus an x to the negative 1. Remember, if you have it at the bottom of a fraction, it's to a negative exponent, so we're going to write that there. And now what we can do is take the derivative of each piece. So over here what we're going to have eventually is the derivative 3 times the derivative of x. So we're going to have, let's just do that with the arrow, 3 times d dx of x, which would be 3 times 1, or just 3. Over here, the derivative of a constant is always going to be 0. And over here, we're going to use that power rule. So we're going to put a negative 1 in front. We're going to say x, and then we're going to say the negative 1 minus 1, which is going to be negative 2. And we're going to rewrite that as a negative 1 over x squared. Remember, if you have the negative exponent, you must put it to the bottom of the fraction. And we rewrite all of this, and we can safely say that dy dx equals 3 minus 1 over x squared. Okay. The last 2 topics I want to show you. The first is finding the slope of a graph. Remember, that's all derivatives really represent. They represent how much a function is either increasing or decreasing. They represent the slope of a function. So, if we were given the example, we were asked to find the slope of the graph, and it tells us the graph is f of x equals x to the 4th, and we were asked to find this for x equals negative 1, for x equals 0, and for x equals 1. Well, the first thing we have to find, remember, we want to find the slope of the graph. We know we have to find the derivative in order to do that. So, our f prime of x, our derivative, we can use the power rule here. We put our n in front, we write our x, and then we do to the 4 minus 1 to the 3rd. Cool, so we got our derivative. Now, what we have to find is the derivative at each value, the slope at each x value. And we can do that by substituting in these values for our x. So f prime of negative 1 would be 4 times negative 1 cubed, or 4 times negative 1, which would be negative 4. F prime of 0, we would get 4 times 0 cubed, which would end up being 0. And f prime of 1, we would get 4 times 1 cubed, which would be 4. Alright, so these would be our slope values for each x value that we substituted in. And I want you to understand something. Since our slope here is negative when x equals negative 1, we know that our function, fancy f, is decreasing. We know fancy f is constant if our slope was 0. And we know our function f was increasing at this point of x equals 1 if the slope is positive. Let's prove that graphically real quick. Let's graph x to the 4th. Get your coordinate plane going. We'll call this one negative 1. We'll call this one positive 1. And we'll go up 1, 2. Okay. So we would have a point at negative 1, 1, and we have a point at positive 1, 1. And our graph would sort of do this. Oh, let's make sure we have a point at 0, 0 as well. Okay. Our graph would kind of do this. It would come down and it would get kind of flat. It wouldn't be a very pretty curve. It would just get kind of flat at the origin, and then it would curve back up. Okay. That's what it looks like. And our tangent lines would be doing the following things, right? Because what we found just now were the slopes of the tangent lines when x equaled negative 1, when x equaled 0, and when x equaled positive 1. And so we can see our answers made sense. It does look like this is decreasing pretty rapidly. I believe that the slope is a negative 4 over 1. And at 0, it is a perfectly horizontal line, which does represent a slope of 0. And then here at positive 1, again, we're increasing pretty sharply here. So it does make sense that this would be an increase of 4 over 1. All right. Last topic to show you, and I'll leave you alone. Finding equation of the tangent line. You may be asked to do this in an unconventional way, in a way we haven't discussed previously, so I'd like to go over an example of such a thing. Say we're asked to find an equation of the line of the tangent line to the graph of f of x equals x squared when x equals negative 2. Okay. Find an equation of the tangent line to the graph of f of x equals x squared when x equals negative 2. So, remember from before when we found tangent line equations, we did so because we had a point and we had a slope from our derivative. Right now we don't have a full point, we only have an x value, but that's okay. Right? We only have 2, and we don't know what our y value is, but we can find our y value if we substitute into our f of x. So, f of 2 is going to be 2 squared, which is going to be 4. Alright, so now we know we do have a point of 2, 4. Pardon me, negative 2. Negative 2, 4. Now what we can do is we can find the derivative in order to get that slope. So we can say that f prime of x, we're going to use the power rule. We're going to take that 2, our n value, we're going to put it in front, and we're going to say x to the 2 minus 1, or x to the first, or just x So our derivative is 2x. Now, furthermore, we want to know when x equals negative 2, what the slope is going to be. So we're going to derive that. 2 times negative 2, and we get negative 4. Awesome. So we have two key pieces of information. Right now we have a point at negative 2, 4, and we know we have a slope of negative 4. So what we can do is use this information. We can substitute into our point slope form. If we have y minus 4 equals our m value, negative 4, times x minus our negative 2. Okay, so what we can do now is distribute that negative 4 out. We get y minus 4 equals negative 4x. This negative times a negative 2 would become a positive 2. Negative 4 times positive 2 is negative 8. We add our 4 to both sides. We get negative 4x negative 4x minus 4. And there we have it, the equation of the tangent line. Okay, that's all I have to show you. Thanks for watching.